Hi everyone, and thank you for joining this webinar on slide 3. My name is Alison McQuillan, Director of Rocscience Australia. I'm a geotechnical engineer with nearly 15 years of open pit mining experience based on the Gold Coast in Australia. Today we're going to show an example application of slide 3 for an open cut coal mine setting. However, the model build process, search functions, and interpretation tools we will show in this webinar can be applied to any slope stability analysis. The example application will be demonstrated through a pre-recording, which will be later uploaded to Rocscience's YouTube channel. First, let's discuss when and why to model in 3D. In my view, geotechs should look to model in 3 dimensions if any of the following 3 conditions are met. If pit slope geometry is 3-dimensional, if the anticipated failure mechanism is 3-dimensional, or if material strength is anisotropic, such as highly bedded or jointed rock masses. The following are a list of recent publications demonstrating the application of slide 3 to mine slope stability analysis. Each of these papers includes applications of slide 3 for the conditions highlighted on the previous slide. That is, to repeat, conditions where the pit slope is 3D, conditions where the failure mechanism is 3D, and conditions where the material strength is anisotropic. Okay, let's start the example. Throughout the video, please enter any questions in the chat box and we'll endeavour to answer them throughout the recording.
Hi, in this video I will show you a demonstration of building a slide 3 model using geometry files typical of an open cut coal mine. First we need to import the geometry files we want to include in the model. Let's go to Geometry, Import, Import Geometry, and select the files that we want to import into our model. In the Import Geometry menu, you can repair or clean each piece of geometry you want to import, or you can import directly and then clean within the software. In this example, I'm going to import directly. If you want to view the geometry you have imported in Section View, select the Section Cut tool. Next, we should view the quality of each geometry entity to be included in the model and repair if required. I'm going to start with the topo surface and hide all other entities in the model. Then go to View, Show All Edges. And then go to Geometry, Repair Tools, Repair. Here you can see this piece of geometry has several issues that may result in the entity not dividing into the model. We will select Repair. We want to repeat this process for all pieces of geometry in the model, aiming to have 0 defects for each geometry file. It is important to also compare the repair piece of geometry with the original to ensure no appreciable deviations in the shape and detail of the original wireframe as a result of the repair process. Now we've cleaned all our geometry, I'm going to turn Show All Edges off. Now we need to define an external boundary. There are multiple ways of doing this, including using the Create External box, Create External from Surface, importing a volume and setting as external, or creating your own volume in slide 3 and setting as the external. In this example, I'm going to create our own volume. Go to Geometry, Polyline Tools, Draw Polyline. Ensure you are in top view and then draw the polyline within the topo surface. We will then modify the polyline so the Z coordinate is above or below the topo surface. In this example here, the Z coordinate of 200 is not enough for the polyline I've created to be completely above the topo, so I'll edit again. We'll then convert the polyline into a polygon by going to Geometry, Surface Triangulation Tools, Create Triangulation from Closed Polygon. Now we extrude this polygon to make it a volume, ensuring it extends below the base of our topo surface to the desired model depth. Geometry, Extrude, Extrude. In the Z direction, I'll now assign our newly created volume as the external. Like slide 2, we need to have an external boundary defined in our model before defining material boundaries. Next, we want to divide all. This is to convert the surfaces in our model into volumes. In this example, we want to include the topo and roof and floor of our coal seams in our model. I'll first divide all by the topo surface only. All entities that are assigned as a geology will be included in the divide all process. If you don't want to include a piece of geometry in this process, change its role to construction. It'll now be my external polygon and my topo surface that are included in the divide all process. I'll now remove this excess piece of geometry that's been created by the divide all process that sits above our topo surface. I'm going to change its role from geology to construction, and then select that piece of geometry. Geometry, discard selected construction geometry to remove it from my model. I'm now going to divide all by the coal seams in my model, changing their role from construction to geology, and divide all again. Let's look at the volumes that have been created in 2D section view. Can you see that our lower coal seam has not had a volume defined? Let's investigate why. If we re-import the roof and floor of this coal seam, compare it to our topo surface, you can see that the roof of the D12 seam does not fully intersect the external or any other surface that's in our model. In such instances, new volumes will not be created. In our slide 3 model, I'm going to manually insert a new plane just inside the boundary of the current D12 roof, so a closed volume should be created for the D12 seam when I divide all again. Another option would be to modify the D12 roof surface to extend beyond the external and then redivide. This looks better now we have a D12 seam in our model. Zooming in on our newly created volume for the D12 seam, understand this is a pretty sharp edge for the D12 seam, which is likely not true in reality, but conforms to the geometry files that were imported and divided all into the model for demonstrative purposes. Depending on how uniform or undulating the surfaces of entities are that are imported into the model, it is recommended you check the number and the location of small volumes that were created after each divide all process. Select Geometry, Repair Tools, Collapse Small Volumes. You can view in terms of a user-defined volume or using the Advanced Filtering tool. In this example, you can see a number of small volumes, all less than 100 cubic meters, that if collapsed from the model will be insignificant to the calculation process. These entities are not deleted from the model, they are merged and assigned the same material property as the surrounding volumes. Now let's assign material properties. Go to Materials, Define Materials. I want to define material strengths for spoil, weathered strata, fresh coal measure rock, coal, joints, and faults. The material strengths entered here are for demonstrative purposes only. Assume 2 persistent joint sets are modelled in the advancing high wall that I want to include in the model. After I define strengths for fresh rock and joints, I'll create a new material called Jointed CMR and define generalized anisotropic properties with joint strength in plus or minus 5 degrees of the dip and dip direction of the mapped joints. My base material will be fresh coal measure rock, and my anisotropic strength material will be joints. The dip and dip direction of the 2 joint sets I want to enter are 80 and 115, with an A value of 5 and a B value of 5, and my second joint set will have a dip of 84 degrees, dip direction of 56, and an A value of 5 and a B value of 5. I use a B value of 5 degrees to indicate that outside of the orientation of joints, there is a relatively quick transition to fresh rock strength. So joint set A, joint set B. After defining material strengths, we need to assign them to the volumes that we have created. We can either assign them by selecting the volume from the active window and selecting the material property, select the volume from the visibility tree on the left-hand side and assign the material property, or by using the Assign Materials Using Cutting Plane, which creates a 2D section through the model. You can see in Section View that I have two volumes of the same material that were created when I divided ore using the manually inserted plane to create a volume for the D12 scene. To refine and reduce the number of entities in the model, we can select these volumes and union. This is an optional step. We have previously defined strengths for faults. Now we need to assign the fault surface that we previously imported as a weak layer with fault strength. I'm going to hide all other entities in my model and make the fault visible. Can you see that when we've imported our fault file, there's actually two faults in the one piece of geometry? I'll show you how to split these into separate geometry entities using the tools in slide 3. Select the fault file and ensure its role is geology. Then go to Geometry, Surface Triangulation Tools, Ungroup Non-Manifold. This tool will separate non-manifold triangulations into separate manifold surfaces. This process has now created several new triangulations that we can merge back together into separate fault files. You can see when I select these individual triangulations, there's actually small gaps between each of these surfaces. When I merge it by going to Geometry, Surface Triangulation Tools, Merge, I'm going to change the tolerance option from Low to Custom and enter a larger value here. And then repeat the process for the other fault. I now have two fault surfaces. I'm going to assign each fault as a weak layer by going to Materials, Weak Layers, Add Weak Layer Surface. I'm going to rename it Fault 1 and assign it Fault Properties, and then rename the second fault Fault 2 and assign Fault Properties. I'm now going to turn all my entities back to full visibility. Before computing, we need to select an analysis method under Analysis, Project Settings. To find the global minimum, it is recommended to select all 4 analysis methods, as the optimization function uses critical slip surfaces generated from all selected methods. Then select Surfaces, Slip Surface Options. For this example, I will select Ellipsoid and run an optimized cuckoo search. Depending on the size of your 3D model, you may want to increase the number of slip surfaces that are generated by increasing the number of nests or iterations, or include a search limit to concentrate the slip surfaces that are generated in a specific area of interest, for example, at a bore nose, along a shear plane, or where faults daylight in the slope face. To include a search limit, go to Surfaces, Add Search Limit, and in this example, we'll add a search limit by box. Then move the box to the area of interest that you want to concentrate the slip surfaces in. In this example, I'm going to select completely inside, which means all slip surfaces that are generated should fall within the box I've defined. Now let's compute. Let's look at the results. We can cycle through and see the different critical factors of safety that were calculated with each analysis method. In this example, the GLE and the Spencer methods produce a very similar factors of safety, and the Bishop and Yambu analysis methods also produce very similar locations of critical factor of safety. When interpreting results, we recommend viewing all slip surfaces that have been generated during the calculation process using the Show All Surfaces option. This view option shows both the spatial distribution of slip surfaces that have been generated and where clusters of low factors of safety areas have also been calculated in the model. The surface safety map is also a great display tool to summarize the distribution of low FOSS areas across the slope. A different contour map will be created for each analysis method. And you can customize the contours on the right hand side. To view results in 2D, select the Section Cut tool. And move the crosshairs to the location you want to cut the section in. The critical FOSS will be displayed on the 2D section. I'm now going to add a water table to the model and compare the 3D factor of safety with the 2D factor of safety on the low wall side. Select the Geometry tab, and then select the water surface that was previously imported and change its role from Construction to Geology. I'm just going to make this visible and hide all other entities in the model. I created this surface in slide 3 by using the Polyline tool and digitizing a polygon that would be representative of the water table. Similar to the Create External Volume process, I then converted this polygon into a surface by using the Create Triangulation from Closed Polygon tool to create a surface. To assign this surface as water table, select it, and then go to Groundwater, Add Water Surface, OK. I now have a water table assigned to my model. As I want to analyze low wall stability, I'm going to move the location of my initial search limit to the low wall side. And now select Compute. I'm also going to complete a sensitivity analysis of dry conditions in a second model. In this second model, I'm just going to delete the water table. and select Compute. Let's compare results by comparing dry conditions on the left and water table applied on the right. Looking at the critical factor of safety of dry conditions and the factor of safety of saturated, we can compare the results of all methods on the screen by selecting Annotate, Show Method Value Table. As we would expect, dry conditions produce a higher factor of safety across all methods. Let's view results in 2D section to see how much of the low wall is below the water table, resulting in a lower factor of safety in the with water table scenario. Two-D sections can be cut in slide 3 and 2D factor of safety calculated and compared to 3D results. To generate slide 2 sections, select slide 2 section creator. I'm going to create a single section and cut in plan view. Directly through my critical factor of safety area. I can also select the direction I want slide 2 to calculate the factor of safety. In this example, left to right to calculate on the low wall side. After selecting OK, my 2D section is now displayed in the viewports. I can then go to Analysis, Slide 2 Integration, Slide 2 Compute, and the software picks up the slide license on my computer and computes the Slide 2 file that has been created. Once the 2D compute is finished, we can display both 2D and 3D results in slide 3. "3D factor of safety" and 2D factor of safety. The Slide 2 file is available in your Slide 3 project folder to view and modify as if it were created as a standalone Slide 2 file. It is important to make an assessment of the coverage of slip surfaces and complete sensitivity analyses with different numbers of slip surfaces to ensure you have found the critical FOSS in your model. I'm going to rerun this analysis with a higher number of slip surfaces. By increasing the number of slip surfaces, the software calculates a similar critical factor of safety. But more low factor of safety slip surfaces are calculated in the northern end of the slope, as more slip surfaces have been generated in this section of the slope with an increase in number of nests in this iteration. Another search tool within slide 3 that can be used to find the critical factor of safety is the Multi-Modal Optimisation tool. This is available for particle swarm searches only, and as the name suggests, searches for multiple local minimas based on the radius span of search space. Now showing the results of multimodal optimization. Using this search setting, we are presented with the results of 3 optimized slip surfaces, which should be useful in identifying multiple low FOSS zones in your model. Let's now look at adding a load to the model. Assume we want to simulate the shovel sitting on the high wall crest. Go to Loading, Add Loads. Enter the dimensions of the load to add, and then select Move Load to the desired location in the model. If you want to move the load once applied, just select the load from the visibility tree and then the pencil icon to edit. Then go to Location and Move Load. Before computing, let's move the search limit from the low wall to the high wall side. And compute. These are the results that were computed, showing the critical factor of safety of all analysis methods and 3 optimized critical slip surfaces. Now to demonstrate how to complete a back analysis in slide 3. For this example, I'm going to use the dry low-wall conditions model and back analyze combinations of spore C and phi that will result in a factor of safety less than 1. For the first iteration of this model, I've run an optimized particle swarm search with the critical GLE factor of safety calculated as 1.77. To complete the back analysis, we go to Project Settings and select Statistics and activate Probabilistic Analysis. I then need to enter the range of potential spore strength in Statistics, Material Statistics. I'm entering in values that indicate spore cohesion could range from 20 to 55 kPa and spore friction angle could range from 15 to 36 degrees. I now select Compute. Once computed, in Results, we will select Statistics, Scatterplot, and want to plot cohesion versus friction angle and highlight all data points that will give a factor of safety of less than 1. Now we can select any combination of C and phi that is highlighted green and re-enter into our slide 3 model. I'm going to select a middle ground combination of cohesion of 33 and friction angle of 20 and recompute. Once recomputed, we can see that this combination of C and phi results in a GLE factor of safety of approximately 1. We can repeat this process with any combination of highlighted C and phi within the probable range of spore strength. Thank you for your attention in this tutorial. For all your technical support queries, please email us at support@rocscience.com. Happy modelling!
If you have any questions, please again feel free to email us at software@rocscience.com or myself at alison.mcquillan@rocscience.com. I'm just going to take this opportunity as well to introduce or remind people about the upcoming Rocscience International Conference to be held virtually from April 20 to 21. Keynote speakers include Dr. Everett Hook, Dr. Will Borden, Dr. Foon, and Dr. Chetan. We'll also be hosting 2 panel sessions on numerical modelling and its integration with monitoring instrumentation. Panelists include a suite of industry godfathers. It'll be a great event, and registration is through Rocscience's website. The Rocscience International Conference is designed for geotechnical practitioners, where papers and panel discussions will have a focus on the practical application of Rocscience software. If you're interested in 3D analysis, be sure to check out our paper, which compares the results of 3D and 2D analysis of a highly bedded slope. A finite element workshop will also be run in the days preceding the conference. This course will be led by Dr. Reginald Hammer, Director of Rocscience Africa, and Dr. Alireza Azami, Geotechnical Specialist based in Toronto. Registrations are again open through Rocscience's website. Thank you for your time today. If you'd like to trial the software or again have any further questions, please let us know. Trust you have a great week ahead. Thank you.